I would like to thank Francesco for the kind invitation and for the opportunity of presenting a part of my research. I will start with a few minutes in a very abstract setting in order to present the principle of virtual power as I have it in mind. Then I will introduce higher gradient continua with a definition which you'll see is only an example of the possibility that higher order materials offer. And then I would like to spend the second half of this presentation on a very specific example which deals with fluids. Okay, so the abstract setting is that of dynamical systems. We say that a dynamical system is a triple, omega, D, and S, where omega is what we call the underlying space, which can be an open subset of R3 in the usual situation, but which could be also any kind of set, a discrete set, a graph, just a singleton on the point. It can be many things. The most important thing is D. D is the space of descriptors which are the fields we use in the modeling, so velocity fields, density, pressure fields, every function space which describes the system we deal with. And usually, from a mathematical point of view, D is a differentiable Banach manifold. As I said, this is a very abstract setting, but we will come soon to more concrete examples. In D, we encode the kinematics. Actually, the kinematics is encoded not exactly in D, but in its tangent bundle or tangent space. If D is contained or is a convex subset of a Banach space B, and for linear theories like linear elasticity or linearized fluids, B is a Hilbert space usually, then for any descriptor U in D, that means for any state of the system, U is a descriptor, describes a state of the system. We have that the tangent space of D at the state U is isomorphic to this Banach space. what does it mean? It means that thinking of elasticity, U is the displacement. Okay. Usually you have boundary condition, maybe Dirichlet boundary conditions. If the Dirichlet boundary conditions are not homogeneous, that means you have a certain data G at the boundary, then the space of possible displacement is not a Banach space. It is only a convex subset of a Banach space. But the virtual fields, the virtual displacement, V, will be in the Banach space H10, let's say. And this Banach space is exactly the tangent space at U of D. So you see that the kinematics, that means the possible states of the system and also the possible evolutions of the system are described by B, and boundary conditions are encoded in D. So the complete kinematics stays within D, the space of descriptors. S encodes the dynamics, the stresses, the forces which are acting on the system. And from a mathematical point of view, S is a section of the cotangent bundle T star D, so that if we compute the stresses on a specific state U, this object is a linear form on the space of virtual fields, because it belongs to TU star D, which is isomorphic to the topological dual of B. Okay, and the total power expended by the system in the state U on the virtual field V is given by the duality SU, a linear form applied to V. And the principle of virtual powers is a way to characterize equilibria, to characterize the state which are the equilibrium configurations of the system. So the principle of virtual power says that U is a feasible state. It means that it is a realistic configuration for our system, if and only if the linear form S calculated on U applied to V equals 0 for any virtual field. Okay, this is a very abstract setting, a very general statement of equilibrium, of the equilibrium condition, which are, if you will, the Euler-Lagrange equations of an energy functional. If you have an energy functional, then SU is the first variation of the energy computed at U, and this duality is exactly the weak form or variational form of the Euler-Lagrange equation. Now, this introduction was to emphasize two things. That the kinematics is encoded in D, first thing, and second, that the dynamics deals with the linear functional on the space of virtual fields. Okay. Usually, the tradition in continuum mechanical modeling is to start from physical considerations and to build S, to describe the stresses as function of the displacement or velocity field or density, and then to write the equations. And V comes from maybe the mathematical trick of weakening the formulation of the problem. We start from a partial differential equation, you multiply it by a test, you integrate, and then you find the variational formulation. But what is very important, and here I think it's clear that you have to set up from the very beginning the kinematics, and now we'll see that the kinematics, which means D or the Banach space B, give some important hints on the possible integral representation of the stresses, of the forces. And we will see that there is a strong link on what kind of functional space you choose for the virtual fields and the possible integral representation of the actions which are in your system. So now I will pass to introduce kth order materials as a particular situation, and I will take the reverse path. I will start from the kinematics and then show which is the form of the possible forces or the possible stresses. So assume that our function space B is a Hilbert space HK of a domain omega, and we think of omega as a bounded domain in R3. This is we take a very specific example. Omega bounded domain in R3. We take the Sobolev functions, which have the kth derivative in L2. So I think that all of you knows very well what I'm talking about. Then we have that I said that the possible actions should be linear functionals on the space of virtual fields. So linear functional on HK. And there is a very well-known theorem, Riest representation theorem, which states that for any linear functional f which belongs to the dual of hk of omega, topological dual, there exists a unique function f in hk of omega such that the duality between f and v is equal to sum over e ranging from 0 to k of the integral on omega of the ith gradient of f dotted with the ith gradient of v for any v in hk omega. So you see that in a natural way, if your kinematics requires k derivatives of the virtual field, okay, and in turn, since we have seen that D is contained in B, B is the space of virtual fields, so the kinematics in the virtual fields requires k derivative. As a consequence, also the real field will have k derivatives. Then, if you want k derivatives, all the possible linear functionals can be represented as an integral involving at most the kth gradient of both the virtual fields and some function, which we'll see in a moment, usually is taken in linear theory. In linear theories, this f is just a constant or a constant matrix applied to the real field. We will see an example in a few minutes. So the definition I would suggest for kth order continua in this very specific example where the correct kinematics is described by hk, I would suggest to say that we have a kth order continuum if the total power expended at any state u on virtual fields can be represented by a sum of integrals of that kind. Now, instead of writing gradients, I take generic tensor fields, AI, U, always for every V is understood. And these are tensor fields whose domain is D. The domain is D because we take a state U, then we compute, we associate to any state U not just a matrix but a tensor field with values in L2 from omega to R n to the ith power. Okay, this is just, it's a bit tedious to keep track of all the indexes, but this is just to say that we need to have the correct integrability for such tensor fields. If you just take AUI equal to some constant times the ith gradient of the real field, this is the simplest example. Okay. You can see that for every U, this gives you something in L2 from the domain omega to R and I. So this is my way of explaining the fact that the kinematics gives relevant information on the possible dynamics you can induce on your system. Because in continuum mechanics we have to build models starting from experiments or information from realistic situations, and informations are not always of a dynamical kind. Sometimes we have very clear information about the forces acting on the system, but sometimes we have information related with the kinematics, and we have to use both of them to, in order to understand which kind of power, total power, is a suitable power for the problem you want to study. Now, as you can see, here we have only volume integral, because it is the most natural form of integral representation for that power. But it is also common practice to use surface interactions, contact interactions, and there might be a question asking whether those interactions are encompassed by this framework. And the answer is again in an equivalent representation, which is still which is a theorem, again from maybe always the Riest representation theorem, with no assumption, no additional assumption on our system. We are just saying that V is an HK function, and we want to describe linear functionals on V. We have that the sum from I from 0 to k of the integral on omega of ai u dotted with the gradient V can be in an equivalent manner represented by what I call interaction fields. I will write in a moment what they are, but have first a volume integral of B of U dotted with V, plus a first surface integral T of U dotted with V on the surface. And those are the only terms we get in a first gradient theory. If K is less than 2, you only get bulk interactions or volume forces, volume interactions, and the surface contact interaction. Now, if K is greater or equal to 2, you also have additional terms on the boundary, sum over S ranging from 0 to K minus 2. If K is equal to 2, it's only one term. The integral on the boundary of some M&MoCS dotted with the normal derivative on the boundary of the S gradient of V. And we assume that omega has a Lipschitz boundary, okay, or even the omega piecewise smooth. It means that you only have edges, you may have edges, but then this is a finite union of smooth boundaries, smooth surfaces. Then if you check, S can be only 0 if we are in H2, can be at most 1 if you are in H3, and so on. And this gives you the correct trace theorem, because you have to be able to compute the normal derivative of that field and to take the trace of this derivative on the boundary. And this is all well balanced. But now I take a piecewise smooth boundary, so I have to say something on the singular part of the boundary. If the boundary is, if you have a sphere, everything is regular, and these are the only terms you get. If the boundary has some singular part, which I call capital E, maybe I write here, sum always S ranging from 0 to K minus 2, the integral on capital E of fields K, US, dotted with the gradient S of V. And this term is often referred to as concentrated surface interaction, because actually it comes from a surface integral, but after some manipulation you end up on line integrals. Okay, this singular part is just made up of edges, so it is really a line integral. And this is one kind of concentrated interaction. But let me emphasize the fact that you can see this interaction only if your domain has a singular part in the boundary. So the interaction fields are B, T, MS, and KS. And I would like to write down the correct functional spaces for these fields, which are all respected if we take this kind of tensor fields. So we have that B. Okay, since they are, let's say that they are on the, okay, I'll write them. No. B should belong to HK of omega, with values in R3. This is, of course, if V is a velocity with values in R3, but we can forget about it. What is relevant is the space, and actually B can stay in the topological dual of this space. And everything here stays in a dual. TU lives on the boundary. It belongs to HK minus 1/2 of the boundary dual. What does it mean? It means that since the trace of V on the boundary belongs to HK minus 1/2, and this is given by standard trace theorems, here we can integrate, we can make a distribution act on V, but what kind of distribution? All the distributions which belongs to this topological dual. MS stays in HK minus S minus 1/2 minus 3/2 of the omega dual, and K stays in HK minus S minus 1 of the edges, always dual. Now, if you want later, we can discuss about the surface term, but just think a second on the volume interaction field. If we take K equal to 2 and the space becomes H2 from omega with values, let's say, in R3. V, in this case, as it will, I will use this case for fluids. V is a velocity field in R3, so it has 3 components. With this situation, V is a continuous function because H2 in R3 embeds into a space of Hölder continuous functions, and H2 omega topological dual, since here we have continuous functions, which you know very well, you can prescribe the value of a continuous function at every point of the domain. There is no ambiguity. in saying, in writing the value of a continuous function at one point. And this implies, in particular, that a measure like the Dirac's delta measure concentrated at 0, for example, belongs to this space. Why? Because it makes sense to compute this integral, the integral over omega of delta of x times v of x in dx. Okay, now I should write a vectorial version of the delta, but let's think for a minute with a scalar field, phi, the temperature or something else. This integral has a meaning. We know that it is just equal to the function phi calculated at 0. And this might be a formal definition of the delta function, but we can see that if phi is a continuous function, this definition has a meaning. If phi were only an L2 function or H1 function, it would be absolutely meaningless speaking of the value at one single point. So this is a very important point because shows that a second order power, a second order material has in the natural power or in the natural stresses you can imagine acting within it, it has also very concentrated stresses. And I will give an example, an application where this actually happens. So now I'm going to switch to the fluid part and to the application, but maybe you have some question?
Yeah, okay, maybe this will be object of later discussion, because you prove this representation or you postulate?
No, you can prove this representation, but well, it is really only a matter of Riest's representation theorem, and
it could be interesting to check how this is compatible with Schwarz representation, in which you have only normal derivatives, not normal derivatives of the gradient, surface gradient. That is total grad S or only surface gradient?
no, it's this is the trace on the surface of the S gradient of V.
So you interrupt integration by parts on the surface. Because the Schwarz theorem lets you represent these terms only in terms of normal gradient.
Well, we may discuss it later. Now, I don't know that.
Interrupted your integration by parts like you want. I think what you are writing is correct, but the representation is not unique. In order to have a unique representation.
Okay, this representation might not be unique. You're right. That one was unique. That one with the F.
So forgetting a unique interpretation of interaction fields, you need a unique representation, right? Okay, this will be discussed.
Okay, if you have additional regularity on these tensor fields, you may also prove that B and T and all the fields can be expressed in terms of derivatives of A. But if you don't have the regularity, you still have some field here. Okay. So now I will pass to a more concrete example. I spoke about the total power acting on the system, but usually we consider first an internal power and then an external power, the power of internal stresses and the power of external stresses. And the constitutive assumptions are usually made on the power of internal stresses. And for so I will speak about fluids, incompressible viscous fluids. Incompressibility means that the divergence of the velocity field u, which will be the only descriptor of my system, should be 0. Okay, and the power of the internal stresses, computed at u, acting on a virtual velocity field v, will be represented as a second order power, but requiring, as it is customary, requiring translational invariance and rotational invariance, because we are talking about viscous fluids, and if you make a rigid motion, no friction acts. So you require that your internal power be invariant for a rigid motion. Then you get that the zero order term disappears, and the internal power has only a first order term with a tensor T dotted with the gradient of V, and a second order term with a tensor G, third order tensor, dotted with the second gradient of V. Now the classical constitutive theory for Newtonian fluids assume isotropy and linearity of what? Isotropy and linearity of T as a function of the velocity field. Okay, so, and we end up with T equal to mu, the standard viscosity, times the gradient of u plus the gradient of u transpose. This is the symmetric part of the gradient of u, completely standard term. And then you have a pressure minus P times the identity matrix. If we take the same assumption, linearity and isotropy, on G as a function of what? As a function of the second gradient of V, of U, then we end up with an expression which is not so simple, but not too complicated. We have three new material parameters. Eta 1, eta 2, and eta 3. And you'll see now some combinations which multiply various kind of second derivatives. Three times eta 2, the symmetrized second gradient. This is the symmetrized first gradient, okay, minus eta 2 plus 5 eta 3. The Laplacian of U, tensor product with the identity matrix, plus three times eta 3, the symmetrized version of this term, and in the end we still have some kind of vectorial pressure term minus pi, which is a vector field, tensor product with the identity. What we usually say is that the pressure terms become a Lagrange multiplier of the incompressibility constraint. It means that if you compute this integral and also this integral, this term, and also a part of this term, let's say, a part of this symmetrized term, disappear. Because there is no power, there is no dissipation associated with those three terms. They are there only to guarantee that your flow is incompressible, that the volume of the fluid is locally preserved. Okay, so when we work on constitutive prescription, usually we forget about those terms.
They are Lagrange multipliers
for that constraint. Okay, now you can see that with a lot of assumption, I would say that this is one of the simplest second gradient fluid model, because it's linear, isotropic, but we still have three additional material parameters. And when you make a continuum mechanical theory, you would like to have a physical meaning for your material parameters. Maybe, hopefully, the possibility of make some measure in which you can measure those parameters. But in this case, you go immediately in some troubles because they come out from the assumptions, and you have to think about their meaning only after the fact, let's say. And I would like to present here briefly what I understood about their meaning. And then I will show you what I think is really the simplest model, in which only one of those parameters survives, in which that survivor has a physical meaning. Okay, there are thermodynamical conditions, explicitly the fact that the dissipation must be non-negative. You cannot create energy from nothing, which implies something on those coefficients. Specifically, you have, as usual, mu greater than 0, eta 1 plus 2, eta 2 greater than 0, eta 1 minus eta 2 greater than 0, and the more complicated expression, eta 1 minus eta 2 minus 6 eta 3 minus 2 times the square root of eta 2 squared plus 4 eta 2 eta 3 plus 9 eta 3 squared greater than 0. This is thermodynamics, a physical assumption, but you can easily see that if we take eta 1 equal to 0, then we have to take also eta 2 equal to 0. You just use the first two equations to show it. And less easy to see, but eta 3 should be negative in order to satisfy the positivity of the dissipation. Now, in a previous paper with Marzocchi and Giusteri, we showed that such a kind of fluid gives rise to an equation of motion which is quite nice. We have the divergence of u equals 0, and then rho du in dt, this is the material derivative, equal to the gradient of a modified pressure, which is a combination of those terms, minus the gradient of the modified pressure, plus mu Laplacian of u minus eta 1 minus eta 2 minus 4 eta 3, the Laplacian of the Laplacian of u. With what kind of boundary conditions? Well, you can take various combinations, but you have the natural generalization of Dirichlet boundary conditions, or let's say that we prefer to take Dirichlet on the field U, but since you have higher order derivatives, you have to say something also on higher order derivatives at the boundary. And the full Dirichlet problem would require to say something on the normal derivative of u, but this is often too strong, and we prefer to say something on the normal derivative of the gradient of u. This is just as taking Dirichlet for the first gradient, for the first level, and Neumann for the second gradient, because this comes as a natural boundary condition if you have a sort of variational approach. And okay, we were able to prove not existence and uniqueness of solutions for this equation, because that was already done several years ago by Lyons, Ladyghenskaya, and others, because this term is a quite useful term. it's a regularization of the Navier-Stokes equation, and so you have existence and uniqueness. But we studied the problem of the fluid structure interaction, where the structure are one-dimensional bodies immersed in a three-dimensional fluid. And this is a problem that you cannot treat with the standard Navier-Stokes equation, because of a very simple reason. In the standard case, having only the first gradient in the power, you can only control the H1 norm of the solution. And the H1 functions with values in R3 are not continuous functions. You can, so there is no point in, you cannot state the adherence to a one-dimensional body. The fluid simply doesn't see that object. It's invisible. Okay, it is possible in simple situations to prove that for the standard Navier-Stokes fluid you have a solution of the problem, but in those solutions the fluid behaves just as the structure, it doesn't see the structure at all. It behaves as a free fluid without any structure. This can be computed explicitly. Now, coming back to the meaning of the parameters, I have no clue on eta 2, because if you take eta 1 equals 0, then eta 2 must be equal to 0. In that expression, you see that eta 2 is somehow modifies the relative weight of the symmetric part of the second gradient with respect to the full second gradient, but on its own is not able to produce a physical situation. We cannot have eta 2 equals 0, eta 3 equals 0, eta 1 equals 0, eta 3 equals 0, and eta 2 different from 0. This is impossible from the thermodynamical point of view. So I would just say that eta 2 is ancillary with respect to eta 1. Now, what is very important is that eta 1 equals 0 implies that this term, even for a bundle which is non-smooth, this term is equal to 0. So if you have eta 1 equals 0, you cannot have that kind of concentrated interaction. This was first noted by Francesco and Sepescieri in a paper, and then rediscovered several times by many authors. And I think there is no time to show why it happens, but we made also some explicit calculations in benchmark problems, and you can really compute that K, the tensor, and you can see that it is eta 1 times something. So if eta 1 is equal to 0, that term is 0. And eta 2 and eta 3 don't enter that expression. So eta 1 is responsible for the presence of concentrated interaction of that kind on the edges of singular surfaces. But I like much more eta 3, because you can take eta 1 equals 0, you don't have that interaction. Eta 2 must be equal to 0, then you can take eta 3 negative. Eta 3 negative means that, okay, this term becomes minus 4 eta 3, and this is positive. And so let me just rewrite this term. In that case, it becomes mu eta 3, not eta 3, some, let's say, xi over mu, the B Laplacian of u, and this term is positive, this is positive, so the overall coefficient is minus something positive, and we call this L squared. It has the dimensions of a length squared, and L may have various names. Somebody calls it gradient length. Anyway, it is a length scale. Now, coming to the, which is the role of eta 3. Here we have the thermodynamical assumptions. In the mathematical proof of the existence theorem for the fluid structure interaction, we used an enforced assumption. Here, all the inequalities must be strict, because you have a bilinear form which should be coercive to control the norm of the solution and to prove the existence. But in reality, it would be enough to have eta 3 negative, and also something vanishing here. The only thing is that you don't obtain a solution which is always in H2. You might end up with a solution which is only in a little bit larger space, but which is still a space of continuous function. Since it is a space of continuous functions, and I say that that is the correct descriptor space, so it encodes the kinematics of the system. The kinematics is given by continuous functions, and then in the dual of continuous functions I have concentrated measures. And I can think of studying situations in which I have a concentrated interaction only with this eta 3 different from 0, dropping eta 1, eta 2. In this way, I have only one new parameter, which actually is this length, and not eta 3 in general. We take this combination, is this length is the new parameter, and I would like to end this presentation by showing you the possible physical meaning of this length. So let us consider a very simple problem, which for the classical case was solved by Stokes, I think in 1851. Which is the problem of the steady flow of a viscous fluid at low Reynolds number, which means a linearized version of the fluid equation. The flow past the sphere. Okay, we take the flow past the sphere, and since I know the end of the story, I take the sphere of radius L, exactly, that L. The classical problem, the problem solved by Stokes, has the form of divergence of u equals 0, then it's a steady and linearized problem, so I have only the gradient of the pressure equals mu the Laplacian of u, and I have u equal 0 on the surface of the sphere, and u equal some fixed velocity field at infinity, we call it capital U, now Stokes was able to solve this problem, and in particular he was able to compute the drag exerted on the sphere by the fluid, and the drag is a vector which has the direction of u, and it is proportional to v, and the constant is 6 pi mu, but let me check. Okay, 6 pi mu L, the radius of the sphere, times the vector u. This is the drag exerted on the sphere by the fluid. Now, I considered a problem with a second gradient fluid, which is intended to be an approximation of this problem. And it is divergence of u equals 0, gradient of p equal mu Laplacian of u minus mu L square the Laplacian of u, u equal capital U at infinity, and u equals 0, where this time not on the boundary of a sphere, but u equals 0 at the origin, exactly at the origin which was the center of the sphere. So I have u equals 0 in a point, only at a certain point of the space. And since in this case eta 3 that becomes this coefficient is different from 0, I am able to solve this problem with a non-trivial solution. If I would have written the problem without this term, I would have found a solution, but only a weak solution for which the value at the origin is immaterial, and that weak solution is the zero solution everywhere. You take the zero function, you modify it only at the origin. Since you are in H1, you have again the same function, and it solves the problem, but you don't have any motion. With this term, you are in H2, and you find a function which is not the zero function and has the correct behavior at the origin and also at infinity. And then you would like to compute the drag on the point. Now you have a particle which has been shrunken to a point, and you would like to compute the drag on that point. The point has no radius, but the drag on the point is 6 pi mu L u. Exactly the same. And this is why I like to think of this problem as an approximation, a geometric simplification of Stokes' problem. Because I take a 3D sphere, I forget about the thickness, and I just have a remembrance of the thickness in this parameter. So in this way, I get a meaning for the second order parameter, which was unclear, now is clear. That is the thickness, the effective thickness of your points. You have a point that now can interact and has an effective thickness, because the point is not a physical entity, is an abstraction, a mathematical idea, which here is intended to represent a spherical particle. And to conclude, let's think of which is the force. This is a drag, so it means that the point by reaction is exerting a force on the fluid. That is a concentrated volume force. It's a force which has an impact on the whole space because it stops the fluid, okay? And the presence of the point is felt everywhere, but the force is applied only at the point where you put your adherence condition. Now it is no longer a boundary condition, because the point is not a boundary. It is a constraint on the space of solution, which gives you a convex subspace of H2. And this constraint represents the adherence to the zero-dimensional object. We are also studying the problem of let's say the drag of segments or flat bodies in a fluid, and it becomes a little bit trickier, but of course it's important. And the last development we are trying to tackle is the problem of the free fall of a rigid body, because in that case the motion of the body is not prescribed. You have to couple the partial differential equations for the fluid and let's say the equations for the rigid body motion, and this coupling is non-linear, is a non-linear coupling, and also non-trivial to deal with.
Did you try a solution for a sphere of finite radius?
Yes, the solution for a sphere of finite radius has a term which is the classical one, plus an additional term proportional to L. So there is a correction. Yeah, the drag is modified because you have a three-dimensional body, but your points are thick. You have to think there is always an additional dissipation. So, yeah, maybe you can see it as a boundary layer.
But in that case, the boundary condition should be applied not only on the surface, but also on grain.
Yes, if you have a surface, you have to add something. I don't like to add the full Dirichlet boundary condition, because if you have a flow, let's make a picture. Let's think of okay, we have the sphere in the fluid. The adherence condition says that you must be 0 on the sphere. You can think of your streamlines. If you take the full Dirichlet problem, you have that the normal derivative of u must be fixed on the whole sphere, and maybe 0 since everything is still. Okay, but it means that in every direction your velocity field, its gradient is orthogonal to the tangent plane to the sphere, and it is a very strong assumption. It means that your velocity here goes to 0, but not. I don't know how to picture it, but like this. So it's
a stability condition which allows you to have.
Exactly. What I prefer to use are those, they are called weak adherence condition, but which are essentially the natural boundary condition on the higher order term, which let the normal derivative be free at the expense of having something on the second normal derivative, in essence, or on the Laplacian of u, of the trace of the Laplacian on the surface. It allows the normal derivative to adapt to a more realistic situation, and then you have some smoothness which can accommodate the higher order derivatives. Of course, if you have a boundary, you have to impose additional boundary conditions, and it is not very clear what kind of boundary condition is the best one. It depends upon the properties of the surface. If you want a rough surface, but
In the static case, this has been studied and been requested by ATS. So maybe you can get inspirations in the pure.
yeah, actually, what I'm studying now is the degenerate case more, because I'm interested in simulating particles as lower dimensional objects. And when you shrink everything, you lose the boundary condition. You don't need the additional boundary condition. You have only the adherence. And that is also a nice feature, in my opinion, because also the new boundary conditions are new modeling, new stuff which is not clear how to handle.
In sense, the first gradient fluid does not see an object. If the object is at the lower if it is a surface or a point, the surface do not see this object. If the object is a three-dimensional object, is seen from the first gradient fluid.
Yeah, sure.
Maybe not.
Yeah, if it is two-dimensional, it is seen, but with some problem.
It depends on the orientation. So if you add the length scaling the equation to this new
Yeah, actually, I prefer to see it in this way. I wanted to have continuous velocity field in order to say that the adherence to one-dimensional object. If I want to have continuous velocity field, I need to use a second gradient fluid, because I need to have this term. And as a consequence, I'm able to deal with the fluid structure interaction. But you can see it from one end or from the other end. The main idea is that you want to model some situation and you try to have a good mathematical model for what you're looking at. And we think that the advantage of this approach to the physics or the simulation of particles in fluids is mainly on the fact that you get rid of boundaries. Because think of having awfully shaped particles, maybe hundreds of particles, and you have to use very complicated numerical schemes in order to take into account all the motion. The domain is moving, because when you move a particle, the domain of the computation is moving. If you shrink everything to lines, the domain is just the big box. And the lines are not, do not produce boundary conditions. They only produce a constraint, maybe a time-dependent constraint on the velocity fields, but which can be handled in a different way, also numerically. Even though the numerics is still, we are doing it with a collaborator, but it is not trivial, also the numerics. Thank you. Eta 1 equals eta 2. Yeah, here you have the first, well, it is admissible. You have to control, but in that case, I didn't check. You have to check that the symmetric part of the whole Hessian is enough to control the norm of the...
Did you check this?
No, I didn't.
I guess this is the most interesting question.
I will check it.
Otherwise, you have a local control. Yeah, the quadratic form is locally positive. But if you have just one equality somewhere, you have a curl of some functions. But after integration, it could still be enough to better with boundary conditions. And you have a non-local control, which also will leave something with your boundary conditions. Yeah? If you have a very strong positive quadratic form, you get troubles with boundary layers. If you have a weaker quadratic form, which only after integration and using boundary conditions produces uniqueness, then this will be very interesting. But you didn't check it.
Yeah, I didn't. I checked the situation where eta 3 survives. And it is possible that you have an interplay with eta 3. So it might be different to have eta 1 equals eta 2 and eta 3 0 or eta 3 negative. Because if eta 3 is equal to, if eta 3 remains negative, probably just the same proof is okay also for that case. But if eta 3 is equal to 0, I have to check, but it's a good point, I will check it.
We will discuss, because we are doing some different motion in a second gradient fluid, so maybe we can collapse Gaussian forces. By the way, for you, rho is always constant.
Excuse me?
For you, rho is always constant.
In these incompressible theories,
We are considering rho variable, but without friction. So this could be an interesting interaction.
yeah, of course, also one of the meaning of the abstract introduction was to show that the descriptors and the higher gradients can be higher gradients of many different things. Also, for example, I know about the Cattaneo-Maxwell equations for the heat conduction. That is another example of higher order assumptions to cure.
Gradient fluids are those fluids for which you have compressibility and the deformation energy depends on the gradient of density also. This is the standard type of technology.
Yeah, that's why I added in the title second gradient dissipative fluids, to emphasize that the second gradient is in the dissipation functional, which is basically what you write there.
You are investigating another aspect. Capillarity is everything concerning boundary layer formation in static conditions. So one could investigate what happens to this boundary layer when you flow.